One of the things that we can do with functions, besides using the first and second derivative test to identify the characteristics, another thing you can do with a function is if it's bounded by the x-axis, then going from point A to point B on a closed interval, then we can find the area underneath that particular curve. Now, you can definitely use integrals to easily find the area under a curve, but I want to start with another way that's honestly a little more detailed, and that is estimating area with what's called finite sums. Here's some background information. Hold on just a minute. This is lessons 21 and also 22. A great achievement of geometry was obtaining formulas for the areas and volumes of various shapes. In a previous lesson, we developed a method called integration. Actually, we hadn't talked about how to do that yet. The definite integral, as you'll see in a separate video, is a key tool in calculus for defining and calculating areas and volumes. Like the derivative, the definite integral is defined as a limit. The definite integral is a limit of increasingly fine approximations. And the idea is to approximate a quantity such as the area of a curvy region by dividing it into many small pieces, each of which we can approximate by something simple as a rectangle. Summing the pieces together gives us a pretty good approximation to the original area. And it makes sense as we divide the region into more and more pieces, the approximation will generally improve. And using a term from calculus too, converging to the quantity we are measuring. And we take it as a limit of the number of terms increasing to infinity. So that is the layout of what we're about to discuss. And basically, if you have a curve that goes from A to B, what I just read to you is that you can draw many rectangles and then find the area for each rectangle and sum them up together. This is the Greek letter sigma for sum. And that's one way that you can approximate the area under your curve. Sigma notation allows us to write a sum with many terms in a compact form as seen below. As I mentioned, the Greek letter sigma stands for sum. The index of summation k tells us where the sum begins and where it ends, or the number above sigma is represented by n, as you see here. Now, if you're asked to find the sum going from, like, say 1 to 5 or 1 to 7 of a particular function, I guess you would call it, then that's pretty easy. You just here start at 1, plug it in for k, and then you plug in 2, 3, 4, etc., and then just add them together. But what if you had something that went a lot higher, like you had to find the first 20 terms or something like that? There are some formulas that I'll show you in just a minute. Yeah, here we go. Here's some useful summation formulas. If you're finding the sum going from 1 to n of k squared, then this is the formula that you'll use. If you have the first n cubed or k cubed, then this is the formula that you would use. Hold on just a second. I was looking through my notes here. Now let's look at the first problem. And we're going to find the area under this curve using this particular formula called the alternative form. So let me copy and paste it to our whiteboard. And copy and paste the first question. And it does take a long time to find the area using this particular process. And it's also kind of good to, if you're not given a formula, or not a formula, if you're not given a graph, then go on Desmos and get a graph. So let me go on Desmos and type in our function. And we will definitely have to zoom out. And I'll share my paint board with you in just a minute. All right, let me share my paint board. For the function given below, find a formula for the Riemann sum obtained by dividing the interval going from 0 to 9 into r equal, no, that's not r, that's an n, cut off the n equals subintervals, and using the right-hand endpoint for each c. Then take a limit of this sum as n approaches infinity to calculate the area under the curve over the interval, closed interval 0 to 9. Okay, A and B represent our endpoint, our interval, excuse me. And n we actually do not know, but we can plug in a and b to kind of simplify this just a bit. So we have b minus a over n, which is 9 minus 0 over n, or just 9 minus 0, 9 over n. Now I'm going to plug that in to our second part here. And what that means is that you're taking all of that and plugging it into original x in your function. So f of a plus k times b minus a over n, that is 81 minus a is 0, k is our constant, and we just found the b minus a over n part. That's 9 over n. And your original function is x is being squared. So when we simplify, we got now 81 minus 9k over n quantity squared, and then times the 9 over n. Now we are going to separate this into two summations. And hang on just a second. We can do that and also distribute this 9 over n times everything in our parentheses. So we have, according to the summation formula here, the sum from k equal to 1 to n of 9 over n, we'll pull that out to this in front, of 81 minus 9 over n. The second sum is going from 1 to n of our 9k squared, 9k over n quantity squared. This will take some getting used to because there are, not gonna lie, there are a lot of steps, but most of the steps are mainly plugging in and doing algebra. Now we need to simplify this just a bit more. I'm going to square out the 9k over n. So I'm just going to bring down everything else. And when we squared the 9, that would give us 81 k squared all over n squared. Now, the 81 in the first summation, I'm going to bring it out to the front. Let's see, I'm trying to figure out what happens here. There is a summation rule that I did not show y'all. If you're taking the sum of a constant, then it's just going to be that constant times n, the multiplier. It's like if you were 81, let's say it was going from k equal to 1 to 12. Well, all that means is you're just summing up 12 81s. Or that's the same thing as multiplying 81 by 12. So this part here would be 81n. Now the n's cancel, and when we multiply 81 times 9, we get 729. Now, usually the n part, you pull out and move it to the front of your summation sign. The k is usually the constant, or what we're trying to find. So when I pull out the 81 over n squared and multiply it by 9 over n, that will give us 729 over n cubed times the sum of going from 1 to n of k squared. Now, we can actually find this part because it's a special summation formula. As I showed you earlier, we can replace the sum of k squared with this particular formula. All right, so let me copy and paste it. Just lay it over our k squared. Now let me make some room so we can finish and find the area under our curve. Now, when you multiply n times n plus 1 times 2n plus 1, I'm not going to show it to you here, but that's just a straight multiplication. You should get 2n cubed plus 3n squared plus n, and that's all over 6. Now let's simplify just a bit. I'm going to leave the negative 729 in front and just multiply the denominators. Now we are ready to take the limit as n approaches infinity. Per the directions right here, that's where I got that from. It says, then take a limit of this sum as n approaches infinity. So we are going to do that next. So we will take the limit of everything as n approaches positive infinity. And I'm just splitting this up. And I can actually move that 729 in front of our second limit. Oh, and that should be infinity right here, so sorry. Now, when you take the limit as n approaches infinity of a constant, it's just a constant. So this part right here is 729 minus 729. And I'm going to show you a real neat shortcut. Because our fraction, we have just one fraction here where the numerators share a common denominator. Now I'm going to split this into three separate fractions. So we got 2n cubed over 6n cubed plus 3n squared over 6n cubed plus n to the first power over 6n cubed. And that's going to simplify first fraction or reduce to 1/3 plus 1 over 2n plus 1 over 6n squared. Now we can take the limit as n approaches infinity of each part. The limit of a constant is still that constant as you saw earlier. So the limit as n approaches infinity of 1/3 is still 1/3. Now right here, when you plug infinity in to your second fraction, any number, non-zero number over infinity, know that infinity is a very, very large number. So if you were to put 1 over, let's say, 1 trillion, and it's not going to be exactly 0, but it's going to be pretty darn close to it. So we can assume that any non-zero number over infinity is 0. The same thing happens when we plug infinity in for n with the third fraction. 1 over infinity, that also gives you 0. So we are almost done. 1/3 of 729 is 243. And the area under the curve going from 0 to 9 is exactly 486. Let's look at another problem. Hang on just a second, I'm copying and pasting it. For the function given below, find a formula for the Riemann sum obtained by dividing the interval 0 to 6 into n equal subintervals. Then take a limit of the sum as n approaches infinity to calculate the area under the curve over from 0 to 6. The first step, oh, I forgot my formula. Hang on. Okay, here we go. Now, per our example, A is 0, or the left endpoint, and B is 6, the right endpoint. And I'm going to plug these into our alternate form over here. So we have 0 plus k times 6 minus 0 over n. And keep in mind the f part means that we're actually going to plug what's in the parentheses into our original function. Times b minus a, or 6 minus 0, all over n. So we got part of our formula done. This here at the end, and partially inside, this will be 6k over n. So the 6k over n is what we're plugging into our original x in our function. So let's do that over here. And let's go ahead and square out the 6k over n. That would be 36k squared all over n squared plus n. Now let's plug everything into our alternate form. This part right here that I just boxed in is our 36k squared over n squared plus 7 times the b minus a over n, which is just 6 over n. Now, a couple of things we are going to do. We are going to split this off into separate summations. So 36k squared over n squared times our 6 over n, we're distributing that, plus the second summation going from 1 to n of 7 times 6 over n. Excuse me. Now let's simplify a little bit. Thirty-six times 6 is 216. And n squared times n is n cubed. our summation sign, I'm sorry, that should be k down there, of k squared plus, let's move the 6 over n outside. And we have the sum going from k equal 1 to n of just 7. The second summation, one property of summation is that if you have a constant, you just multiply the constant by the n, whatever the ending number is. So that would just be 7 times n. When the n's cancel and you multiply 6 by 7, you get 42. Now, this part right here has its own special formula. So we'll replace that entire part, summation, with our formula. N times n plus 1 times n plus 2. Oops, sorry. No, that's not the correct last part. That should be 2n plus 1, excuse me, all over 6. Again, not going to show it to you here, but when you multiply the n times n plus 1 times 2n plus 1, you should get 2n cubed plus 3n squared plus n all over 6n cubed, and then plus our 42. Now we're going to multiply just a bit with the first part. We'll just multiply the denominators. So we have 216 times 2n cubed plus 3n squared plus n all over 6n to the 6th power plus 42. And I think I have an extra n cubed. Yeah, I sure do right here. Let me mark that out. Excuse me. So your denominator should actually be 6n cubed. Sorry for that mistake. Now we're ready to take the limit as n approaches positive infinity. And because we got two parts, I'll just separate this into two limits. We have the 216. Actually, I'm going to simplify this. 6 can go into 216 36 times. And we can move the 36 in front of our limit notation. Times 2n cubed plus 3n squared plus n all over n cubed now, plus we got to take the limit as n approaches positive infinity, 42 as well. Now, because our fraction is just one fraction with the common denominator, now we can split our fraction into 3 separate fractions. So we got 36 on the outside, limit as n approaches infinity of 2n over n cubed plus 3n squared over n cubed plus n to the first power over n cubed. Now, this second limit is easy to calculate because when you take the limit of a constant, it's just that constant. So that's just plus 42 at the end. All right, so we have 36. Limit as n approaches infinity. The first fraction simplifies to 2. Second fraction reduces down to 3 over n. And the third fraction reduces to 1 over n squared. Now remember our little rule from earlier. If you have any non-zero number over infinity, then that's pretty much guarantee is getting close or equal to 0. All right, the limit of 2 as n approaches infinity, that's still 2. Three over infinity, that goes to 0 per our little formula here. And 1 over infinity squared is still 1 over a very, very large number, and that also goes to 0. So we got 36 times 2, which is 72, plus 42. So the area under the curve going from 0 to 6 is exactly 114 square units. I'm about to show you to preview the next few lessons. I'm going to show you an easy way to find the area. So we'll do this for the shortcut for our same problem. There is a rule in calculus, it's called the fundamental theorem of calculus, that states if you have an area under a curve, let me just draw a general curve here. Going from A to B, and is bounded by the x-axis, and you're trying to find the area of the region under the curve, then you can use this formula. The integral going from the endpoints a to b of your given function. So let's see if we get the same answer using our area under the curve formula. So let's set it up. Our interval is going from 0 to 6 of x squared plus 7. And as you saw in the previous video on antiderivatives, remember that I rewrote constants with x to the 0 power. Note, we didn't change the value of 7. We just rewrote it a different way because x to the 0 power is 1. Oh, I didn't finish the rest of the fundamental theorem here. When you take the integral, to find the area, you just plug in b first into your integral, minus, then you plug a into your integral, the lower limit of integration. Now, to find each antiderivative, we're going to do the power rule for derivatives in reverse. So instead of subtracting 1 from the original exponent, you'll add 1 to it. And instead of moving your original exponent to the front and multiplying it by a constant, the opposite of multiplication is division. So you'll divide your antiderivative by your new exponent. All right, the next one, we have 7. And again, instead of subtracting 1 from the original exponent, you're actually adding 1 to it. And instead of multiplying, you do the opposite, division. So we'll divide our entire second antiderivative by our new exponent. So we end up with x cubed over 3. And the second one would just be plain 7x. Now we're ready to use our new theorem to find the area under the curve. Now, according to your fundamental theorem of calculus, part 2, by the way, you take your upper limit of integration and plug it into your integral. So that means everywhere we see an x, we'll plug in 6. In between your substitutions, you have a mandatory minus sign. And now the second go around, everywhere you see an x in your integral, you plug in the lower limit of integration, namely 0. Well, actually, everything in the second parentheses goes to 0. So we're just worried about the first parentheses now. 6 cubed is 216 over 3 plus 42. 216 over 3 is 72 plus 42. And we still get the area under the curve. Let's try this same theorem with an earlier problem. Hold on just a minute. The first problem we did was find the area under the curve being f of x equal to 81 minus x squared over the interval going from 0 to 9. And using Riemann sums earlier, we found our area to be not 486. Let's use our fundamental theorem of calculus, and I'll put it over here for us. And let's use this to find the area a little bit easier. So we're going from 0 to 9 of our function 81. And I'm going to rewrite that as 81x to the 0 power minus x squared dx. Again, to find each antiderivative, you undo the power rule for derivatives. Instead of subtracting 1 from the original exponent, you add 1 to it. And instead of moving your original exponent and multiplying it by the constant in front, you do the opposite, which is division. So we're dividing our first antiderivative by the new exponent 0 plus 1. All right, the next term, do the same steps. We'll add 1 to 2. And instead of multiplying, we'll divide by our new exponent. So when we simplify, we get 81x minus x cubed over 3. And we're ready to find the area. According to our fundamental theorem of calculus, part 2, we plug our upper limit of integration into our integral first. Everywhere you see an x, plug in 9 first. Minus sign comes next, always. And the second time around, everywhere you see an x, plug in your lower limit of integration, namely 0. So we got 81 times 0 minus 0 cubed over 3. That entire second part in the parentheses goes to 0. So we now have 729 minus 729 over 3. And 729 over 3 is 243. Got the same area as before. Unless the directions in my math lab state that you have to use the Riemann sum, I don't mind if you use the fundamental theorem of calculus to find the area under a curve. Look for this video in Blackboard announcements either today, later on today, or first thing tomorrow. And also, I know I won't have time to cover it today. So what I'll do is find some type of video from YouTube or Khan Academy to explain how to find the area under a curve using the midpoint rule, as well as something called the trapezoid rule. So I'll find a video or videos either in YouTube or Khan Academy to share with you to finish up lessons 21 and 22.